That works. So I'm going to first talk about really the research goal that we're trying to do here, which is focused on trying to get better constraints on rapid binary pops and simulations. The motivation, the computational tools that we have to do this. I'm going to focus on the dynamical stability boundary, predictions for stripped envelope supernovae, and then the thermal stability boundary and some things that we can do going forward. So the goal really here is to identify observations that will allow us to properly constrain models of stable mass transfer. I don't think I need to motivate this to this particular audience. But to do this, we're going to be using both detailed evolution in the form of MESA and also rapid binary pops in the form of Compass. For those that don't know, I'm the developer on Compass, so that's why I focus on this one. As many of you know, MESA is a detailed 1D, so it's flexible and extendable. You have many different parameter options to test the physics, but it is slow compared to Compass, where the physics is simple, modular, very approximate, but runs very, very fast. And so if we can do this properly, we can make predictions on things like rare events like binary black holes and things like that. But it is intrinsically low detail. The connection to gravitational waves, which is for many people a key area of interest, is that we don't necessarily know what the formation channels are. Floor showed this yesterday, but I really like this plot because it emphasizes that we really don't know what the formation channels are for binary black holes, even though this is a phase of great interest to many people in the community. And this is something that we want to know much better. But to do this, we need a better understanding of mass transfer stability. How well do we know the stability boundary? Not very well. As many people in here know, the old method from Soberman 97 was to use these zetas corresponding to the envelope mass, the response of the envelope, the donor envelope to mass loss. And we had a great discussion yesterday about the limitations of this model. And then a few years ago, Hong Ge, who's in the room, looked at this more improved model for critical mass ratios that account for a lot of the more detailed physics that go on in this mass loss when you don't have immediate instability or stability in your envelope, but you have a delayed effect. However, as we noted yesterday, these models require fully conservative mass transfer, right? So there's no angular momentum loss, and that restriction we find is actually critical. When we compare the effect of the limitations of both models, this plot here shows the fraction of systems that experience only stable mass transfer, both immediately after the first mass transfer episode and also at the end of the evolution before any supernova has taken place. So after maybe several mass transfer episodes. And what we see is that the fluctuation in the amount of just the raw fraction of systems that have experienced stable mass transfer is significant. Something like between 5 and 50%. Just from these uncertainties that are fairly standard in these approaches, right? So even after a single mass transfer episode, the stable mass transfer fraction fluctuates from 5 to 50% within standard modeling uncertainties. So these are things that we really need to know. These are standard modeling uncertainties, and we don't have a good grasp on them, but they have a significant influence even at this very early stage, not even worrying about all the way to binary black holes. How can we use supernova observations to help constrain this? So for those that aren't very familiar, supernova observations come in these different categories based on the spectral lines that you see. So you have your canonical type 2, which are hydrogen rich. You have 1Bs, which are hydrogen poor but helium rich, and 1Cs that are helium poor, corresponding to different amounts of envelope stripping. You also have these 2Bs, which have a little bit of hydrogen at early times, which they interpret as having a thin hydrogen envelope that gets blown away toward the later times in the explosion. But you can interpret this as a continuum of envelope stripping in the progenitors. And so using a volume complete sample of supernova types out to 100 megaparsecs from Leo et al., what we can do is we can use these observational constraints on our population basis, assuming very simplified models of how mass transfer applies to the supernova that we see. So in this very, very simple approach, which is also very speculative, if you have a single star or an effectively single wide binary star up to about 18 solar masses, we think that these correspond to type 2Ps. Anything above that, maybe you have some wind mass loss that doesn't leave your envelope. If you have stable mass transfer, you retain a little bit of hydrogen envelopes. These are your 2B progenitors. Common envelope should strip the entire envelope, leaving you with 1Bs or potentially 1Cs. And then if you have a merger, an evolved merger with a star that has a core, so at least one star with a core, you should have a blue supergiant progenitor giving you an 87A-like explosion, right? This is very hand-wavy, doesn't include a thing, things like wind mass loss or things like this, but as a first-order approximation, this is what we're going with. And what we find in this kind of complicated plot here is that if we try and compare the ratio of channels that have hydrogen-rich envelopes or a little bit of hydrogen envelope or none at the time of the supernova to the observations on the right here. So these These columns here are unraveled pie charts. And as we vary the different kinds of binary physics that go into it, we're changing the column there. What we see, if we kind of squint our eyes, is that things are okay. On a pop synth level, this is kind of pretty good, right? We're not really off by even a factor of 2 in some cases. It's not great, it's not a perfect fit, but our models are doing all right. Yeah, like I said, at the pop synth level, this is fairly reasonable. The first takeaway from this is that none of these models are terrible. So our defaults are kind of close. The second one is that the evolved mergers actually really, really common. So that's this dark blue band here is something like a third of all of our hydrogen-rich supernova explosions. That doesn't mean that a third of type 2s are coming from blue supergiant progenitors, that they're all 87A-like. You might have some relaxation of your progenitor if you have a lot of time passing after the merger. But it means that a lot of the supernova models that we see that assume a single star progenitor might be very wrong, right? The structure of the donor, of the progenitor of the supernova might not be that of a single star. And this is not accounted for in supernova simulations. So the conclusion from this is that a pop synth roughly reproduces the observed supernova branch ratios. For now, you kind of have to squint. It's not great, but it works kind of well. But we're really not accounting for more detailed things like post-case B envelope mass loss and partially stripped star winds. So to do this better, we also want to have better observations, but we need to account for these very important physics factors. But then we wanted to explore even earlier than this, if we can get a constraint even earlier in the evolution to see if our rapid pop synth is even doing just the simplest stuff that we think we can do correctly at the level of case A mass transfer. So can rapid pop synth even capture simple case A? The answer is no. So when we look at Compass versus MESA on the main sequence, and we're plotting here, so now we're looking at the thermal stability boundary. And I cut out the slide that discusses thermal stability because I think everyone here is familiar with the zetas that come up a lot in stability discussions. But here we have this thermal stability zeta corresponding to whether your star will, well, in this sort of fiducial model, whether you think it will experience fast case A or slow case A on the nuclear timescale at the initial interaction, at the onset of the first interaction. What we see is that according to MESA, you become less stable with time. So as your star progresses along the main sequence, you're more likely to experience thermal timescale fast case A. Whereas in Compass and other pop synth codes, rapid pop synth, you increase your stability. So you become less likely to experience thermally unstable mass transfer. At the ZAMs, that things are okay, but this is a big qualitative distinction that I don't think has been reported on previously. And this is in direct contradiction to results from MESA. Diving deeper, we were looking into where this problem comes from. And really what's happening is that the way that the rapid models are constructed, where you have, if you have mass loss, you shift to a new single stellar track. This is not able to capture the differences in core structure that you get from detailed codes like MESA. So here I've also included binary C just to emphasize another pop synth code. But really what you see, the important one here is on this M1 dot track. You can see that MESA experiences this fast spike here corresponding to your thermal timescale mass transfer. And neither of the two rapid codes are able to reproduce this. So in short, your rapid codes are not able to match this thermal timescale mass loss. In effect, they're kind of readily producing reverse algals, these systems that are a more massive donor slowly transferring mass into the accretor. They sort of produce too many of these in a sense. But the short takeaway is that these pop synth codes are systematically mistreating the stability boundary. This is something that it is potentially very a major problem. What can we do about it? Well, option A is to do what we love to do in pop synth, which is to find some prescription. You know, we run MESA, we figure out what the core mass is after doing these runs a few times and say, okay, cool. If you have these two masses in this interaction, here's the core mass. Just use that. Change your mass and then you're good. This is a bit hacky, but everything in pop synth is hacky. Option B is to build up a whole new pop synth model that takes into account a more refined core definition and structure. Things like having, maybe some kind of fit to a core that isn't just here's your core mass, here's your envelope mass, but maybe something that's more detailed than that, where you can fine tune it to more detailed stellar models and try and account for some of these more subtle differences. The second option is much more time consuming, probably a lot more work and hard to convince people to do, but also more accurate and maybe the best long-term option. But I'll let the community decide what to do. Either way, this this result only impacts case A mass transfer, so it shouldn't have such an impact on systems that start interacting on case B or case C. However, given that 50% of stars above 40 solar masses are not the main sequence, this likely has an impact on many of the major POP-synth predictions that we're seeing, especially because people don't really look at K-say as a major uncertainty in POP-synth. So just to conclude, we find that we're not modeling the dynamical stability boundary in POP-synth. This has an immediate effect on the post-interaction systems that we're not accounting for. POP-synth roughly reproduces strip-enveloped supernova, but we need better observations and theory. And POP-synth systematically overpredicts the thermal stability of donors on the main sequence, meaning even K-say systems are biased. We need to quantify the impact of this bias, and we also need to decide as a community what to do going forward. That's it.
No one else? Okay, awesome. Yeah, I knew K-say sucked, but now I know it even more, at least in population synthesis. But I didn't really understand. I loved your plot of the zetas with the green for compass and the red for mesa, but I didn't really understand why it's so mirrored. And this might be too detailed, but
why it's so
an
weird.
exact mirror of each other.
Yeah, they're
I mean, the age is going to be roughly the same. It's just subtle differences in the evolution of the code. I would say, I don't necessarily see a mirror to it. It's more that the POP-synth ones are becoming more stable, so they're going to move up, and the diesel ones are moving down.
which yeah.
Okay. Yeah. I don't know. I want to understand why it happens this way. It looks this way. If that's a long answer, we can talk.
Why
in the
is it
copy break.
steeply opposite as you
Yeah.
go up in mass? I think that's the
Yeah.
statement. Like, why does the steepness continue as you increase in mass? It's like
For POP-synth.
Decrease even.
for both,
It's very
they
extreme.
more steeply disagree
And then
as you
they-
increase it.
Yeah.
It's more like when you increase in time, right? The closer you get to the
Yeah.
terminal age main sequence, the more extreme it gets.
I don't know if I can give you a good short answer on that one.
Okay. Let's talk.
If you cut the x-axis in half and sorry. I'm just saying maybe as you were saying, maybe also it's a matter of plotting because of course they live less. So if you actually cut the x-axis, you will see not to the same stiffness, but it's also a matter of the time scales for the evolution. Just saying.
Yeah.
Hey, I fully agree that one should never do K-say mass transfer with a fast code. So next of my question may not make sense, but in POP-synth you have these tracks that are for stars that are, well, not in all POP-synth codes, but in the two codes that you're showing here, it's based on the Hurley tracks. So you always have stars that are in thermal equilibrium. And so I think a lot of magic comes from when you strip the star, what is the next track that you're going to and where on that track do you get? So this result, can it maybe be related to how you decide which track and where on that track you're going to?
It is exactly that result. So by those choices, that's how you get these curves. That's how they're plotted. It is a good question if we can do better by choosing differently, whether choosing a different mass track. So you're supposed to lose a certain amount of mass. Maybe you lose more or less, maybe we change that. Or if you choose a different evolutionary phase that you get to. But these decisions are
yeah, so it's how do you model rejuvenation? Like in physical terms, you're trying to do rejuvenation by adjusting the tracks.
You match the main sequence fractional age.
Yeah.
So if you are 50% along the main sequence, you lose the amount of mass that you're told to lose. You drop down to that new mass, and you're 50% along the new main sequence. So you effectively re-age the star.
I'm kind of assuming that Compass and Binary C do that in the same ways that Hurley recommended.
Compass does some funniness, which you can actually see here. The fact that they don't quite match. Binary C, this is what we were talking about yesterday, pumps up an artificial wind. So it's very, well, it's sort of weakly sensitive to the overflow rate. So what you see is that Binary C can be quite a bit over its own Roche lobe for a long period of time before that wind really makes a difference. But then it will still shift down to a new track and re-age in that process. Compass does this without doing the wind. It will say, what is the Roche loop size I need to fit into? And then just pop down to that new size. So it's sort of like having a very large wind artificially in one time step, but they're both, I mean, they're both doing it wrong.
I mean, this was my question. So
Okay.
If at some point you said there's two options to go with, just as an announcement, we are working on option B of creating a way more detailed and well, taking way more things into account in interpolation tables in binary C, which will be released soon.
Fantastic, we should talk.
it's also in Matisse.
Yeah, Matisse does something similar.
Okay.
Matisse will not solve this.
Something similar. But let him go first. I will talk about something else. So as long as it's consent, let him talk. Go.
And just to, as a follow-up to what we were saying before, I mean, not to spoil my talk, but actually the problem with dropping down to an evolutionary track when you're losing mass during the main sequence is also like a great problem, because, I mean, after you are losing mass bit from mass transfer or like LBV wins or whatever you want during main sequence, I mean, population synthesis prescribe a completely wrong structural evolution, because it's just prescribing like lower mass supergiants, while instead you should go to the other side of the HR diagram and become like for Wolf-Rayet stars. So yeah, I mean, just saying post case A evolution in the population synthesis kind of like wrong.
I agree.
Can I ruin the pop synth party and just switch a bit something else? So when talking about supernovae, it's always a bit of a madness. One thing that I can suggest is that, for example, you talk about the mergers that will lead to peculiar type 2p supernovae, basically. I think you can already split them in basically two classes, those that were undergoing case A mass transfer and merged, because in that case, they become a main sequence.
That actually contributes to our effectively single mass fraction. So this includes case A mergers. We don't even distinguish those because
then they would just be type 2p supernova at the end. They would just evolve as main sequence. Yeah, okay.
more so than the case BC mergers, yeah.
Yeah, not as bad as in the case of BC mergers, because in that case, they may become blue supergiants. Yeah. But then it's also very complicated. Like, do you also sample with different initial masses? Like, how high up do you go with the initial masses when you populate these supernova types?
Pop synth is not really well defined above 50 solar masses. Some people will push it above that, but it's not really supposed to be. Yeah.
Because then from 30-ish to 50, you should expect full stripping. So in that case, it would all be one.
So this is actually an interesting one. We don't know what this lower mass bound is for where you get a fully stripped supernova progenitor. That one we focused. This one you can't really see here. M-min Wolf-Rayet is this minimum mass where you form a Wolf-Rayet, so you lose the envelope before you have collapse. This is very closely related to the missing red supergiant problem, where you see red supergiants up to 25 solar masses, but not as type 2p progenitors. You only see up to 18 solar masses. Some people have suggested that means that you lose that envelope mass between 18 and 25. But it's quite an open problem. So we looked at what that changes about the rates if you allow these single stars up to 25 to retain their hydrogen envelopes. It didn't solve the problem, at least at this level of coarseness.
So then at the very end, just very quickly, you cannot predict the other types of supernovae. So the very fancy ones, like the superluminous ones, or
we didn't look at superluminous. We looked a bit at distinguishing 1Bs and 1Cs, but even observationally, yeah, even that level is almost you're kind of pushing the observational distinction too far. Then they don't even have that quite figured out yet.
That's fine. Thank you.
I do want to make one comment on the red supergiant problem, which is that there are kind of two red supergiant problems that get discussed. One is that there don't seem to be red supergiants anywhere above a certain luminosity. And the other is that when you look at the population of type 2 plateau or type 2 supernovae, hydrogen-rich supernovae, that have then an observed progenitor, and you compare that to the population of red supergiants in the field, there might be sort of an upper luminosity cutoff or an upper luminosity sort of an upper mass limit on the ones that we then see explode, which I don't think winds, unless they're winds that only happen in the last decade, can explain that. So the fact that you don't reproduce that solution to the problem with population synthesis is not surprising at all.
I agree. It could be eruptions, but yeah, we can't model at that level of detail.
Right.